Hi, I'm Jon Stapleton with CodeVA, and this is a quick lecture explanation of mental models or notional machines. It's a computing pedagogy concept, and I'm gonna talk about it a little bit for you right here. Let's jump right in. So code is a series of instructions for a computer to execute. When programmers read code written in a programming language, they'll often trace through the code line by line, imagining what the computer would do at each stage of the program. This is called code tracing, and it's an important skill to develop as you work on becoming a fluent code reader and code writer. Predicting what a program will cause a computer to do is a critical programming skill. It involves thinking about each component of the code systematically and imagining what the computer would do in order and in the order the computer would do it. When you trace code in this way, you're creating an imaginary computer, one that exists only in your mind. It reads the code step by step, and you can use it to predict what the written code might cause a real computer to do. This imaginary computer is called a notional machine, or a mental model of the computer. Your mental model is the computer you imagine running code when you trace through a program. If your mental model is accurate, that is, if it behaves in the same way a real computer would behave, you will be able to run a program in your head to predict how a computer would interpret it. Writing software involves writing some code, tracing through it with your mental model to see if you think it will work correctly, and then testing your assumptions by running the code using a real computer and kind of comparing those two results. If the real computer's behavior matches your mental model, you can keep writing new code. If the real computer behaves differently than your imaginary one did, however, you need to debug your code and update your mental model so it matches the real computer better. Then you can try again. This cycle happens over and over when someone writes, tests, and revises code. They may not realize it, but mental models play a very important role in supporting and informing your computing problem-solving skills. When students begin learning to code, they may have incorrect, unrefined, or misleading mental models of how code controls the way a computer behaves and what sorts of problems computers can even solve in the first place. As students develop programming skills, one of a computing educator's primary goals should be to help them evaluate their mental models and help them build on those models to support more sophisticated understandings of the computer and the code it executes. Next, I'm going to talk about 3 different kinds of mental models that students might develop kind of in sequence as they move from novice programmer skills to advanced or intermediate or advanced programming skills. The first thing I'm going to talk about is sequencing. When students first begin learning to code, they should be able to show evidence of a mental model or notional machine that conceives of a computer as follows. I'm just going to describe it. Quote, a computer is a machine that follows instructions written in code in order, one after another. I can always predict what a computer will do when it follows these instructions, as long as I can look up or memorize what kind of output each command prompts the computer to display, or what kind of input the command directs the computer to collect. As a part of these instructions, the computer can manipulate data stored internally in its memory. Students who have a well-developed mental model at this stage of their programming literacy will be focusing on the following cognitive tasks. They'll be interpreting the commands written in a given programming language. They'll find variables in programs and trace their values as the computer makes operations on them, maybe modifies them over time. They'll be able to predict the results of programs that include arithmetic expressions, including those which include variables as operands. They'll be able to substitute values of variables into those expressions and predict their output. And they'll be able to write programs that take input and produce output using variables and arithmetic expressions. As students develop, they'll start to learn this idea of selection, especially after they learn about conditional control structures. The selection mental model is as follows. A computer is a machine that can make automated decisions. The computer makes decisions based on data stored in its internal memory and rules expressed in code. A computer can only make decisions based on instructions written in code. So, if a programmer wants a computer to make complicated decisions with a lot of possible results, they'll need to write a lot of code. I can always predict what a computer will do when it makes these automated decisions as long as I can read the rules it follows and predict the input data the computer will use to select the code that it executes. Students who have a well-developed mental model at this stage of their programming literacy will be focusing on the following cognitive tasks. They'll be interpreting conditional control structures, like reading if statements or while loops and figuring out what they mean, identifying which lines of code a computer will select from a conditional control structure given different input data. So they'll be able to interpret maybe the relational expression that the computer is using to select different blocks of code. They'll predict the results of programs that include conditional control structures and relational or logical expressions, and they'll begin writing programs that make automated decisions based on input data, producing different behavior depending on the input data provided by the user. The last mental model I'll describe here is a mental model that takes into account abstraction. And this kind of comes after students begin learning about functions and functions with parameters. A computer is a machine that follows instructions, stores data, and makes automated decisions. Computer instructions are difficult for humans to write, so when I write code for a computer, I use programming languages, frameworks, libraries, and other abstractions to make the computer do what I want. I can also write my own purpose-built abstractions to help organize my code, avoid redundancy, make debugging easier, and design systems to accomplish my goals or solve problems. The abstractions I choose to use and the way I design my own abstractions have a big impact on how I am able to approach computing problems. Students who have well-developed mental models at this stage of their programming journey will be focusing on the following cognitive tasks. They'll be tracing functions and methods, stepping in and stepping out of a function to predict what the function causes the computer to do. They'll be interpreting functions with parameters, including tracing their values in and out of the function context or function scope. They'll be writing functions to represent abstract tasks the computer should complete, designed around a specific goal, usually as a component of a larger system that has to do with the problem they're solving with their programming. And they'll be designing abstractions and identifying appropriate abstractions given a problem, or given sequences of code that should be refactored into functions or functions with parameters. Programming pedagogy involves assessing students' mental models and helping them to define those models, identify problems with them, and to guide students toward more sophisticated mental models as they learn more about a given programming language. The pedagogical strategies described in future videos and in the other videos that come later in this course that offer some ideas for helping students develop mental models as they work hands-on with coding languages and tools. If you have any questions about this content, if you have any ideas you want to share, please get in the comments below. We'd love to hear from you. Otherwise, good luck and happy coding.